I spent a good part of 1939 convinced I understood, in outline at least, the only way a black hole could ever come to exist. A star runs out of fuel. Gravity wins the argument it had been losing to nuclear fusion for millions or billions of years. The core collapses past the point where any known force can stop it. And if the remaining mass is large enough, nothing halts the collapse until you reach what we now call an event horizon. That was the picture Hartland Snyder and I worked out mathematically, and for decades afterward it was essentially the only mechanism anyone seriously discussed. Black holes were the corpses of massive stars. Nothing else in the universe seemed capable of producing the conditions required to make one. I want to tell you why that confidence turned out to be premature, and about an idea that emerged only after my death, one that suggests black holes might not need a dying star at all, that some of them, possibly a great many of them, could have formed before any star ever existed in the first fractions of a second after the universe itself began. The idea is called a primordial black hole, and to understand why physicists eventually took it seriously, you have to think differently about what a black hole actually requires. My 1939 work, and everything built on it afterward, assumed a specific pathway. Matter needs to be compressed by gravity, and gravity needs a sufficiently massive object to work with. And the only obvious way to assemble that much mass in one place under normal conditions is inside a star that has spent millions of years accumulating and fusing material before finally collapsing. But there's another way, in principle, to compress matter to the required density, and it doesn't need a star at all. It needs the universe itself, in its earliest and strangest moments, to do the compressing for you. The theoretical case for primordial black holes was developed most substantially by physicists working well after my own death. Stephen Hawking, among the most prominent, along with a physicist named Zel'dovich, working independently in the Soviet Union, both arriving at similar ideas around 1966 and 1971, respectively. Their arguments started from what cosmologists had already established about the very early universe. In the instance after the Big Bang, the cosmos was not a smooth, uniform soup of matter and energy. It had irregularities, tiny variations in density from one region to another. Some areas slightly denser than average, others slightly less dense. These irregularities are, in fact, essential to how the universe eventually took the shape we observe. Without them, gravity would have had nothing to grab onto to eventually pull matter together into galaxies, stars, and everything else we see in the sky. Ordinarily, these density fluctuations were small, fractions of a percent above or below the average density of the early universe. But Hawking and Zel'dovich both realized something important. If a fluctuation happened to be large enough in a small enough region at exactly the right moment in the universe's earliest expansion, gravity could overcome the tremendous outward pressure of the hot early universe and collapse that region directly into a black hole. No star, no stellar evolution spanning millions of years. No supernova, just a region of the infant universe, slightly too dense for its own stability, collapsing under its own gravity within moments of the Big Bang itself. The physics required for this is genuinely extreme, and I don't want to understate how narrow the conditions have to be. In the very early universe, matter was compressed to densities and temperatures almost impossible to describe in ordinary language, conditions closer to the interior of my own equations describing stellar collapse than to anything we could recreate with billions of years of stellar evolution. For a region to collapse directly into a black hole under these conditions, the density fluctuation needed to exceed a fairly demanding threshold. something on the order of tens of percent above the average density, rather than the far smaller fluctuations that eventually seeded galaxy formation instead. Most regions of the early universe never came close to this threshold. But given how enormous the universe was, even in its first fraction of a second, and how many independent regions existed within it, calculations suggested that at least some regions plausibly could have crossed that threshold, especially if certain conditions in the very early universe, particular phases of cosmic expansion, or transitions in the fundamental forces as the universe cooled, briefly made large fluctuations more likely than they would otherwise have been. What makes primordial black holes theoretically distinct from the stellar black holes I originally described isn't just when they formed, but what range of masses they could plausibly have. A black hole formed from stellar collapse has a minimum mass set by the physics Snyder and I work through. You need enough mass for gravity to overwhelm neutron degeneracy pressure, which sets a floor somewhere around a few times the mass of our sun. There is no comparable floor for a primordial black hole. In principle, a region of the early universe could have collapsed into a black hole with a mass far smaller than any star could ever produce. Some theoretical work has considered primordial black holes as light as a mountain, packed into a region smaller than a single atom, formed purely from the extreme density of the infant universe rather than from the gravitational collapse of any star. At the other extreme, some versions of the theory allow for primordial black holes far more massive than any single star could become, potentially offering an explanation for an entirely separate puzzle that had bothered astronomers for decades: how supermassive black holes, like the one at the center of our own galaxy that I discussed in an earlier conversation, managed to grow to millions or billions of solar masses within a period of cosmic history that seems, by ordinary stellar accretion, almost too short to explain. I find this idea remarkable, and I want to be honest that I never once considered it myself. In all the years I spent thinking about gravitational collapse, my own work assumed the universe already contained stars, already had billions of years of stellar evolution behind it, before any black hole could form. The idea that the black hole formation process I described might have a competitor, one that operates on a completely different timescale, using the raw density fluctuations of the newborn universe instead of the slow burn of stellar fusion, simply wasn't part of the framework I was working within. It required cosmological ideas about the structure and evolution of the early universe that were, in 1939, decades away from being developed with any real precision. The modern picture of the Big Bang, of cosmic inflation, of the specific physics governing the first fractions of a second of the universe's existence, none of this existed as a rigorous framework during my working life. Snyder and I could describe how a single collapsing star behaves under general relativity with real confidence. We have no comparable framework for describing the density structure of the universe as a whole in its first instant. For decades after Hawking and Zel'dovich proposed the idea, primordial black holes remained a genuinely speculative possibility rather than an established feature of cosmology. And I think it's important to be honest about that distinction, because the story of how this idea gained more serious traction is itself instructive about how physics actually progresses. The theory was elegant, mathematically consistent, and solved several puzzles simultaneously if it turned out to be true. But elegance and internal consistency were never enough on their own to establish something as physically real. I learned that lesson myself, watching my own 1939 predictions sit largely unconfirmed for decades until instruments finally caught up to the mathematics What changed gradually was a convergence of several separate lines of evidence, none conclusive on its own, but collectively suggestive enough that primordial black holes moved from a curiosity discussed at the edges of cosmology conferences to a serious candidate explanation for several genuine astrophysical puzzles. The first puzzle concerns dark matter, the mysterious substance that appears to make up roughly 5 times more of the universe's total mass than ordinary matter does, inferred entirely from its gravitational effects on galaxies and galaxy clusters, but never yet directly detected in any laboratory despite decades of dedicated search. For a long time, the leading theoretical candidates for dark matter were exotic new particles, hypothetical objects with names like WIMPs or axions, particles that would need to exist beyond anything described by the known laws of particle physics. But after years of increasingly sensitive experiments failed to detect any of these hypothetical particles directly, some physicists began asking a more conservative question. What if dark matter isn't a new kind of particle at all? What if at least some portion of it is made of primordial black holes, objects that are, in a sense, entirely ordinary in their physics, governed by the same general relativity I worked with in 1939, but simply invisible because, like any black hole, they emit no light of their own? This idea has real appeal, precisely because it doesn't require inventing new physics beyond what we already understand. It only requires that the early universe, under conditions cosmologists already believe existed, produced enough of these small, invisible objects to account for the gravitational effects we attribute to dark matter. The challenge has been narrowing down what mass range of primordial black holes could plausibly account for a meaningful fraction of dark matter while remaining consistent with everything else we've observed. Because primordial black holes of certain masses would produce detectable effects we haven't actually seen, effects like gravitational microlensing events, where a black hole passing in front of a distant star would briefly and measurably brighten that star's light as the black hole's gravity focuses it, or effects from black hole evaporation, since Hawking's own later work showed that sufficiently small black holes should slowly lose mass and eventually evaporate entirely through a quantum process now called Hawking radiation, meaning very light primordial black holes formed early enough in cosmic history might already have evaporated away entirely by now, potentially leaving observable signatures in the process. The second line of evidence that pushed primordial black holes back into serious consideration came from an entirely different direction: the direct detection of gravitational waves. First achieved in 2015 by the LIGO Observatory, decades after my own death, using instruments of a precision I genuinely could not have imagined during my working life. LIGO detects the ripples in space-time produced when two massive compact objects, typically black holes or neutron stars, spiral into each other and merge. And some of the black hole mergers LIGO has detected involve black holes with masses and characteristics that some physicists have argued sit somewhat awkwardly within the standard picture of stellar black hole formation. Certain detected mergers involve black holes more massive than standard stellar evolution models comfortably predict should be common, or involve black holes with very low spin, a characteristic some theoretical work suggests would be more expected of primordial black holes formed directly from early universe density fluctuations than of black holes formed through the more complex spin-imparting process of stellar core collapse and subsequent accretion. I want to be careful here because I don't want to overstate the certainty of this evidence, and the honest scientific position, even now, is that these observations are suggestive rather than conclusive. Standard stellar astrophysics has its own explanations for unusually massive or low-spin black hole mergers, dense stellar environments where black holes form through more complex, indirect pathways, and simple, isolated stellar collapse, hierarchical mergers where smaller black holes combine repeatedly to build up mass over cosmic time, and other mechanisms that remain entirely within the framework Snyder and I originally described. The primordial black hole explanation is a genuine competitor to these standard explanations for certain specific observations, not a settled replacement for them. What I find most compelling about where this field has arrived decades after the questions I originally asked in 1939 is the humility built into how the strongest proponents of primordial black holes actually present the idea. Nobody serious in this field claims to have proven that primordial black holes exist. What has changed is that the idea has moved from a mathematical curiosity, an idea nobody could test, similar to how my own 1939 prediction sat untested for decades, into something genuinely testable, with specific, falsifiable predictions that current and near-future instruments are capable of checking directly. Gravitational wave observatories are being refined specifically to detect the characteristic mass and spin distributions that would distinguish primordial black hole mergers from stellar ones. Searches for microlensing events using ever more precise astronomical surveys continue narrowing down exactly what mass ranges of primordial black holes could or could not account for meaningful fractions of dark matter, ruling out large swaths of the theoretically possible parameter space with each new survey. And more precise theoretical work on the physics of the early universe continues refining exactly what density fluctuations would have been required, and how plausible those specific fluctuations actually are, given everything else we understand about cosmic inflation and the conditions of the early universe. I think about this open question the same way I thought about the years between publishing my own 1939 paper and finally learning, had I lived long enough to see it, that instruments would eventually confirm stellar black holes were real and not merely a mathematical curiosity. The honest position at every stage of a genuinely open scientific question isn't confident assertion in either direction. It's careful specification of exactly what evidence would settle the question, followed by the patient, often decades-long work of actually gathering that evidence. What strikes me most about the primordial black hole hypothesis, considered against my own original 1939 work, is how it reframes a question I thought I'd already answered completely. I believed, and I think most physicists of my generation believed, that we understood the complete catalog of ways a black hole could form, stellar collapse, full stop, with the only remaining questions being about mass thresholds and the details of the collapse process itself. The primordial black hole hypothesis suggests that catalog was never complete at all, that alongside the black holes formed from the deaths of massive stars, there may be an entirely separate population formed not from stellar death, but from the birth pangs of the universe itself, existing since the first fraction of a second after the Big Bang, silently populating the cosmos long before the first star ever ignited. If this hypothesis turns out to be correct, even partially, it would mean that some of the darkest, most invisible objects in the universe are also, in a strange sense, the oldest, older than every star, older than every galaxy, older than nearly everything else we can observe in the cosmos, dating back to a period of cosmic history so early and so extreme that even the physics I spent my career working through only begins to describe the conditions involved. I never got to explore that particular implication myself, But I find something fitting in the fact that the same mathematical framework Snyder and I built in 1939, describing how a massive star collapses into a black hole, turned out to be only one chapter in a much longer story about how black holes can come to exist in this universe. A story that, as it happens, may have started writing itself before there was ever a single star in the sky to collapse.